Log on, tune in, find out. Another good idea from Cambridge.
He's come all the way from Harvard. He's Professor of Biological Oceanography there. He does research on ocean and climate sciences. And he's also President of the American Association for the Advancement of Science. So very much involved in making science applicable and understandable by everybody, really. And it's really great that you've come across. Thank you so much for coming across the Atlantic. We're going to offset your carbon, you'll be glad to know. And we look forward to your talk on the denial industry, as you can see.
Excellent. So I didn't choose this title. I welcomed it, and the more I thought about it, the more I worried about the term industry. I give a number of public talks a year. I talk to industry groups, I talk to religious groups, I talk to all sorts of business investment groups. I talk to the lay public, and of course I talk to students, and I'll come back to that at the very end. And to label what I think was beautifully summed up by Sir John in his slides, the problem with the denial that we encounter, and I have to say it kind of rang in a few of the questions we just heard as well. People who have a difficult time accepting the climate science, and we don't, it's very, very, I think, hard and I think difficult, just not quite right to impute motives, although at times it's tempting. But certainly when I talk to religious leaders and I talk to business people and I meet this sense of denial, it's coming obviously from very different directions. So to call it an industry is perhaps a bit too, suggests some organization or some concerted ideology that would be constant across these different groups. I think that probably isn't the case. What I'd like to talk about is a bit of climate science going back to some of the very earliest days. Skip very quickly through some of what Sir John was discussing, and talk about, again, what we see today. I'm going to refer to them as sort of the wedges, the contrarian wedges in the denial industry today, if there is an industry. So Sir John, in a question, talked about what some people call the conservative nature of the IPCC, and I understand where that's coming from, and certainly if those of you who are scientists know that anytime you would get more than two scientists together to talk about something that might result in a position that would go public, and no scientist wants to put his or her name on something that looks like it's out on the edge of the data. No scientist wants to face his or her peers accused of having overread the data, having overstated it. And so the tendency is to draw back a bit. And this is one of the reasons that I have recoiled in discussions in my country where the press loves to refer to the people I'm calling the climate science contrarians, those who do drive the denial business, as skeptics. And I just refuse to let that community have the title skeptic, because every good scientist is a superb skeptic. Our entire career, from its earliest days, is built upon a very healthy sense of skepticism. We're constantly asking if what stands as the body of science is really correct. Is it complete? Are there omissions? Is there a new way of looking at things that would cause us to see science differently than our mentors did? And the whole process of science education, the whole process of science advancing is to be questioning whether what has been laid before us as understanding is sufficiently complete, whether we can add to it because we've asked the right questions. So to suggest that scientists are somehow accepting and climate scientists are accepting of some body of information that others with the title skeptic are more credible to challenge is really ludicrous. I would just like to also comment that I agree completely with Sir John. He ran three cycles, heroic. No one has committed their life to the IPCC the way Sir John has. I feel lucky to have survived one cycle as a co-chair. But to suggest that there's politics in that process is also ludicrous. It would be easy to stand at a distance and say, well, there must be political interference, but I can tell you that overt political interference is so untolerated by the collective of delegations from hundreds of nations that it really, in my estimation, is not a factor. Now, in the area of contrarianism in this business, I just should also add that a little over a year ago, a Channel 4 presentation in this country in the great global warming swindle has yet to be shown in the United States. It's been shown in Australia, but is a real serious abuse of climate science. I will actually, as I develop the paper I'm working on, draw some examples from that, but with Sir John and others, I've been part of an official protest that has challenged the misrepresentation of the IPCC and of the science. At least one scientist who is included in that film, our colleague Carl Wunsch from MIT, threatened a lawsuit, and his segment was removed when the film was shown in Australia. But it's an example of how, and in the United States, the only way people have seen parts of this film is on that wonderful invention called YouTube, the web. And it's an example of how, in some cases, the web is a wonderful instrument to find all sorts of information, and of course, a lot of the information is unreliable, so it's sometimes hard to know when you see information on the web to what degree it is consistent with science and to what degree it isn't. So there's a lot being made this next year, and certainly the big annual meeting of the American Association for the Advancement of Science will be celebrating the 150th anniversary of Darwin's publication, The Origin of Species, the 200th anniversary of Darwin's birth. But there's another interesting coincidence. In 1859, it's the year that Sir John Tyndall discovered that carbon dioxide was a greenhouse gas. 1859, by coincidence, this is, I usually have some notes here that display, no, I'm fine. I use a different, on my computer, a different presentation scheme. So of course, I won't belabor the point. So John talked about greenhouse gases, and I love this cartoon of the insulating blanket, but also in 1859 we had the first commercially viable oil well. So it was 20 meters deep, produced 28 barrels a day, and in the very same year then that Darwin was advancing a new understanding of how life and environments co-evolved on this planet, we have the discovery of the power of an atmospheric constituent to really change the condition of the environment. We have also, of course, the first commercial deployment of a technology that is going to dramatically affect the abundance of that constituent in the atmosphere as time goes forward. But within a couple of years, we've lost the label here. This is Titusville, Pennsylvania. In a couple of years, this is what that part of Pennsylvania looked like. So once oil was discovered, and the realization that this had a great potential commercially, you can see that people wasted no time in charging ahead with this new. Sorry, there we go. Okay. So in 1896, Slodge Arrhenius was the first to calculate the possible effect of accumulating CO2 from the combustion of fossil fuels on Earth's climate. And this surprises people now and then. It's been much written about. There's been some nice histories. In fact, the current IPCC report, its first chapter in Working Group 1, I recommend it to you if you want to know about the history of climate science, because it summarizes this quite nicely. And yet it surprises people because I can't tell you how often I've spoken to people in the United States about this topic, and they have the sense that this whole idea was invented by Al Gore. before Al Gore, there wasn't any greenhouse gas effect, nobody knew about it, and so Arrhenius advanced this idea, and others worked with it, but a person who spent a fair bit of his career refining this idea was Guy Callender. And his publications were in the 30s, late 30s, and in the 1940s. Note that he died in 1964. I'll come back to that in a bit. But he advanced the idea. He of course was without the benefit of carbon dioxide data, but he had temperature data. He saw the rise in Earth's temperature in the early part of the 20th century. He knew carbon dioxide was increasing. Didn't have a precise estimate of that. But he continued with detailed calculations to project where we might be going with this. Now Arrhenius's projections were that if the Earth's atmospheric content of carbon dioxide were to double, the average temperature on the surface of the Earth would increase between 4 and 5 C. That was an 1896 estimate. Now, he also thought it might take thousands of years to get there because he had no idea how good we'd be at this. But the fact that his calculations were kind of within a factor of 2 is really quite astonishing. Callender generated similar types of calculations. And this all changed rather dramatically in the late 50s when Roger Revelle, who had himself, as an oceanographer, a lot of work on the carbon cycle, become really concerned that we didn't have direct measurements, we needed them. He was convinced. He said our society is performing a great geophysical experiment. And of course, all experimentalists know that if you design an experiment, you need a control. We have no control for this one. We have only one planet Earth. And he hired Charles David Keeling, bright young chemist from Caltech, to think hard about this problem. And of course, Dave Keeling generated the initial time series on the volcano Mauna Loa, Hawaii, largest volcano on Earth, high on the flanks of the inland side of the volcano. And today we talk about the Keeling curve. And of course, these stations are not just from Mauna Loa, but now from, in fact, Keeling, I think the second station was at the South Pole, but now a series of stations from high latitude northern hemisphere, Point Barrow, Alaska, all the way to the South Pole. Mostly islands away from local influence. And you see the trace of this upward, this rise of CO2. The seesaw pattern is the annual inhalation and respiration. Inhalation with photosynthesis and releases respiration of carbon dioxide. And at different locations, the amplitude of this is different because of vegetation patterns, but the slope is the same no matter whether you're at the South Pole or the mid-latitudes or high northern latitude, because of the mixing. About a year to completely mix these gases in the atmosphere. So it doesn't matter that most of this is being emitted in the northern hemisphere. What we know is that it's mixed and you can see it anywhere. Now, one of the most remarkable developments in this whole area in my scientific lifetime is the understanding that we have a past climate from the ice cores. And shown here on the far right in that red upward band is the Keeling curve, now compressed from 1958 to 2000 and extending back in time to 800 AD, about 1,000 here in this graph. You see triangles and circles and whatever. These are the ice core reconstructions of carbon dioxide in the past. These all happen to be South Pole stations, but if you look at Greenland data or glaciers in the Andes, you could have the same representation. That for something in the order of 1,000 years, CO2 is rather constant in the atmosphere. The beginning of agriculture, large-scale land use changes, early 1800s, the combustion of coal, and then as we move upward, you see that the ice core data now seamlessly link with the direct measurements of the greenhouse gas, the carbon dioxide network in the upper right. So when these data first emerged, again, they surprised many people, and I'll show you some other in a moment from the ice cores. And we begin to see some of the doubt about the credibility of science emerge with critiques of this, saying, well, you can't possibly trust the measurement of a small volume of gas which was frozen into the trap in interstices of the snow and then frozen in ice, compressed in the glacier. A lot of debate in the scientific literature, but I think today this is an area that those who are looking for something to pick apart have a very difficult time because the science is so robust. This is a representation of the ice core data from the Vostok ice core in Russia, which until a few years ago had the oldest ice, a little over 400,000 years old. There's now ice going back, Pika studied back to over 600,000 years. But you're familiar with this, I'm sure, if you look at the far right, on in the blue curve, we have carbon dioxide, the current level rising with that steep rise, and then going back in time, hundreds of thousands of years, we see the last glacial period about 20,000 years. Is there a pointer right here?
You could use the, because we're next door as well.
Oh, yeah, right. I thought about that, and then you're right, that didn't work. All right, so back in time, we see the carbon dioxide decline, which was the last glacial period about 20,000 years ago, then rise. You go back in time, previous warm period, it's in this seesaw pattern. This was so totally unanticipated. When this emerged in the mid-1980s, I could say that in some parts of what we call now global biogeochemical cycles, earth science, earth system science, this had an effect rather like plate tectonics did in the geosciences. Suddenly, things made sense that didn't make sense before. It allowed us to see the degree to which greenhouse gases had really affected climate cycles of the past. It was very clear that the only way you could move carbon around this rapidly, from going from the cold to the warm periods, involved the ocean. Very interesting questions there, and the sense that the cycles of climate in the past, driven by the orbital properties of the Earth-Sun relationship, were interplayed with this, was a new and exciting discovery. So Sir John showed some recent data from the IPCC. The top panel here is the trend in Earth's temperature. This is from the 2007 report, and we see it bobbling around from the beginning of this series in the late 1800s, rising in the early 1900s, 1910, 20, 30, into the 40s. This is, of course, now the period when calendar is busy with his calculations. And then we see a decline, sort of level off for a couple of decades, and realizing that Guy Callendar died in 1964, perplexed, because in fact, something he thought he really understood for a decade and a half or 2 decades before his death, the atmosphere, the temperature of the atmosphere was not behaving the way he thought it should with this rise in carbon dioxide. We see it now increasing from 1980s, temperature increasing onward. A little summary on the right, 2005, hottest year on record. The 14 hottest years all occurred since 1990, 24, the last 25 occurred since 1980. And the point that Sir John was making about recent years is there's this very high point up here, a high circle, which is 1998, which was the year of the most intense El Nino that we have known in recent climate history. And so there are some who say, well, I can draw a straight line through those last 10 years, so I think climate is stabilized, temperature's not going up. That's frankly just plain silly. You could draw straight lines through any 5 or 10 years along here. It is that long trend we need to look at. And I won't say more about sea level. Sir John mentioned this, the red line in the second panel are the direct measurements from satellites, and of course snow cover and ice cover in the bottom panel declining. So this is a complex figure that's sometimes referred to as the smoking gun. This is in some cases, we have from direct measurements, in other cases from proxies, moving from 1880 forward, the cumulative effect of the changes in the atmospheric properties that would force positively, that is make warmer, or negatively make cooler Earth's temperature. The red curve at the top is the one that Sir John was talking about, is the greenhouse gases, all greenhouse gases. The jagged blue one below is that of volcanoes. And volcanoes are always in the long-term history of climate science. We know that at times volcanoes have had dramatic effects on climate. 1884 is Krakatoa. If this went back in time further, 1815, Tambora. That was the year that had massive crop failures in the area where I live in New England. There was a freeze, April, May, June, July, August, September, October. Crop failures, famine, scale of today's population, about 1 million people died of starvation as a result of the cooling effect of one fossil volcano. 1991 is Pinatubo in the Philippines, 82 El Chicho Lagoon in Mexico in 1963 or 4, and Santa Maria in Costa Rica. So these effects are pronounced, and they are short-lived. Now, there are other factors in there. This blue line or magenta line that tails off at the bottom are the tropospheric aerosols. Sir John mentioned putting SO2 into the upper atmosphere. Well, SO2 in the lower atmosphere has the same effect. It does reflect sunlight, but we also know that it is devastating on the human respiratory system and on natural ecosystems and on buildings, so we've made serious efforts to get that out of our industrial streams, get the sulfur out of stack gas. But the little wavy lines, the brown line in the middle, that's another one that frequently comes into question here. That is solar variability. And I just ask you to look at that little wiggle line since back to 1880. And you can see the amplitude on the units on the far left, about plus or minus 0.2 units. Totally swamped by the insulating effect of the greenhouse gases. Does solar variability affect climate? Certainly it does, over longer periods, maybe more than it has recently. But there is no credence to an analysis of the energetics of the atmosphere driven over the last 20, 30 years, this period of unusual warming, by solar variability. And we know these numbers really well since 1980 because satellites orbiting above Earth's atmosphere have been able to get precise estimates of solar variability, a variety of proxies, C14, Brilliant 10, you can go back in time. So when this is all assembled, this is where we see whether climate science really has it together or not. These are from IPCC graphics in 2007. The upper panel has a combination of that jagged dark line, which are the observations of temperature, and the band of sort of rust color with a red line moving through them are model simulations of this atmosphere starting at 1900 going forward with those forcings from the previous slide. So you see the volcanoes with the vertical lines here, Pinatubo, El Chichon, Lagoon, Santa Maria. You can see the downward spikes as a result of the atmospheric aerosol and a reduction in the Earth's temperature for a year or two. If these did not match up, you would say, back to that earlier graphic, we're missing something. There's something in the fundamental forcing of the atmosphere that's missing. Or we've got it wrong, solar variability wrong, greenhouse gases. If you look at the lower panel, this is the solar plus volcanic forcing in the blue line and the blue band. In other words, leaving out those atmospheric constituents that we know are being influenced by human activity, the greenhouse gases and the aerosols that come from activities. You can see you've got one that fits pretty well, very satisfying. Again, many laboratories have done this around the world, many different climate models with a highly studied set of forcings. And if you take the human component out of that, the temperature in the period we're in right now should be cooler by the difference between this blue line and the black line. So this is the kind of product that I think makes all of us who've worked with the IPCC really proud to have been part of that organization and see the degree to which it has brought clarity with this sort of analysis. So I've looked at a lot of opinion polls that many of them from my country and some international. And so in my country, if this question is asked, has the average temperature of Earth increased over the past century, you get pretty high percentage yeses on that now, you know, 80, 85, maybe 90%. Then when you ask this question, is this warming due mostly to natural cycles and processes? And the next question, is this warming due mostly to human activities? Things get really muddled. And you know what? I don't know how to answer those two questions, because they're not the right questions. First of all, it doesn't say over what period of time. If it said over the last 20 years, I'd give you an answer that I'd be really confident in. If you want the last century, then you'd want to be clear what you were talking about, how early in the century, mostly natural, the latter part of the century, mostly anthropogenic. So I think, and as people look at these opinion polls and then form their views, I think, unfortunately, the subtleties of the science are such that they don't allow you to make a lot out of an opinion poll that would weight the first one at a certain percentage and the latter one at another. And unfortunately, there are people who would argue that these are all or nothing. Well, scientists can't say exactly how much of the warming is due to human activities, so I'm going to discount it. Well, it's to say, you know, I can't say exactly how much of your persona is a result of your genome and how much of your environment. It doesn't mean that one is unimportant and the other is only the other is important. One's 59, one's 41%. What do we make of that? So this is often used divisively when I think it's really quite unnecessary. This winter, the denial industry had a heyday with our cooler winter. Snow cover over North America, much of Siberia, Mongolia, China, greater anytime since 1966. There was a lot of, if you look at the web, you'll find this stuff all over the place. People say, oh, well, we knew, you know, look at the IPCC data, temperatures level the last decade, and now we got this vicious winter, things, you know, going back into a cooling period, don't worry. Here are data, actually from, let's see, the 31st of May, which is the last time I pulled this down. These are satellite data. It's from about 1,000 meters, 900 millibars, it is 1,000 meters. And this is January to December, the Earth's temperature. The sort of squiggly orange line at the top is 2007, and this is average for the whole Earth. It kind of looks like the Northern Hemisphere because of land dominating the Northern Hemisphere. So it has more of an annual cycle than the Southern Hemisphere, which is dominated by ocean. And then you see the red line starting on the left and being discernibly colder than 2007. This is 2008, the red line, bobbing around, and the final point there in May. So yeah, globally averaged, the early part of this year was a cooler year. The yellow line at the bottom is the average for the last 20 years. So yeah, it's a little colder than 2008, but if your memory had all the years back to 20 years, you would have had an average that looks like this lower bottom line. So still a warmer year, but cooler. But this is something that the denial industry had a great deal of fun with. So I'd like to say just a couple things about the Arctic. The Arctic, in addition to the IPCC, I spent a couple years working on the Arctic Climate Impact Assessment. Some of you may have been involved in that as well. I concluded its work in 2005. The Arctic is the region, if you wish, of the globe that is showing the most rapid temperature change. Here is from the 2001 IPCC projection. This is a mid-range scenario projection. Sir John showed a fan rising up to 2100. We take sort of an average, or a middle point. In other words, definitely not a worst case. We see temperatures in the Arctic rising 6 or 8 C, that's annually average temperature. You notice all across Eurasia and North America. And And of course, a primary reason for that, there are a handful of reasons, but one of the primary and easily understood reasons is just the reflectivity. Snow and ice reflects a lot of sunlight back to space. 90%. Open water or bare or vegetated soil only reflects about 10 or 20%. Sea ice. So on the left shows sea ice in 1979. This is September, the month of minimum sea ice. 2003 on the right, and I've got a video here which unfortunately did not come through in the transfer. Let's see, this one says we're going to click here. I think we're right here. Yeah, okay. Yeah, okay, I've got both rooms going the same. So what this video does is unfold and show from 1979 to present what's happened to Arctic sea ice, and these are the satellite data. This is now a graph that would show this thing. On the far left, the beginning of these measurements, 1979, zigzag up and down, up and down, up and down, and to draw a smooth line through here, it's about a loss of about 1% a year in Arctic sea ice. And so roughly 30% over 30 years. Last year we lost 20%. Totally unanticipated. No model projected this. No scientists were sitting there a year ahead saying, you know what? Summer of 2007, the Arctic is going to be a very, very different place. So the Arctic this summer, this is the February conditions for sea ice. On the left is the average 1985 to 2000. Just notice the dark blue, that's the ice over 6 years of age. Look at February 2008. The dark blue is a small bit left in the north of the Canadian archipelago. And we're seeing now something that, going back to the cautious nature of the IPCC, this is from the 2001 assessment. I don't think Sir John ever liked this figure. We call it the burning embergram. On the far right is a column which shows something we call risk from future large-scale discontinuities. And if you take the fan of increasing temperature on the left, and you pick a point in time, you come across, you see, you'd have to get up, even at the end of the century, up to a sort of midpoint rise in temperature to get this right column into the ember. What we had in this column was Greenland. Significant loss of ice from Greenland, thought to be very, very unlikely, even a moderate scenario for CO2 release by 2100. And within the period of time from 2001 to 2007, we learned things about Greenland that nobody had imagined. Greenland is changing dramatically. These are earthquakes in Greenland. The far left in the green bars, about 5 per year in the early 90s, and now they're about 30 per year as of 2005. As earthquakes, ice is moving and the earth is shaking as a result of these sudden slumps of ice. So just to conclude then, Sir John showed a figure somewhat like this. There are a handful of areas that I'm developing in the paper for this seminar that looks at what I'm calling the contrarian wedges. One has to do with, well, it was warm during the medieval optimum, colonies in Greenland, and then cold during the Little Ice Age. I mean, that's natural. Why should we think that what we're seeing now is not natural? Isn't it true in the Antarctic ice that carbon dioxide concentrations do not precede temperature concentrations, vice versa? Something, a point made in the Great Global Warming Swindle. Therefore, carbon dioxide increase does not cause temperature increase. Temperature increase causes carbon dioxide increase, and we can discount everything the IPCC has said. There are questions raised about the satellite data. Don't they show something different from the land surface measurements? The question about solar activity. Can't solar activity, I've seen some very convincing graphs. Great Global Warming Swindle does a great job of this at the end of 1980, and they call it Today, as if you could make draw some conclusion from that. You could, and it's wrong. What we know is that the science is increasingly clear on this. And this diagram is one of an example, a little different from the one that Sir John showed, of how there is no perfect solution to the problem we have, but there are many solutions, and many of them applied properly will get us where we want to go. And I'd like to conclude with a statement about my own statement of optimism, and it comes from my experience, 3 decades now, of working closely with young people, and particularly the last decade where I lived in one of Harvard's clusters, which we call houses, I lived with 400 students. And I must say, in the last decade, 12 years, the remarkable change in interest of young people in this problem. And the realization that this is a defining issue for their generation. The realization that what they do in their lives, no matter what walk of life, to work towards a solution to this problem is going to be one of the most important things they can do for not only themselves personally, because it will be very gratifying, but for the human race and the future of their children and grandchildren. So I will conclude there. Thank you.
I've been part of various people trying to change attitudes to climate change among the general public. I once stood outside the NatWest Bank and gave out flyers about the fact that they were funding lots of investment in oil and things like that. I came across lots of people who argued with me. One in particular was an elderly lady who just said, I can't see, climate change, the weather changes from year to year, so how can you draw any conclusions from it? And I think that's the fundamental problem that we have, at least in Britain, that you can't say that June is always sunny, because it isn't. So, yeah, how do we manage to communicate to people that there really is a change when all they can remember is 1 year to the next?
Well, that is a big challenge, and frankly, I think it has become easier. As we went through a period about the 2000, 2002, and 3 when the press seemed to lose some interest in the subject. And I, with other colleagues and seminars with people from the media, print, television, radio, they all think, well, what are we going to do? Write down the headline, global warming is still happening? I mean, this is not a catchy thing. But that's changed. It has changed. As we have seen records broken. So we have flooding in the middle of the United States right now. The press are getting this right. It's a 500-year event. This is not a typical flooding situation. When we look at the heat wave of 2003, when you look at Arctic ice loss, I mean, if you go from 1% a year for 3 decades, then 20% in 1 year. Now, some of the contrarian press had a heyday with that. They've been saying there was more ice being formed down the Arctic any time in the past. That's true, because you start with more open water, so you can form more ice. So all of this stuff can be spun. But I think the drumbeat of intense storms, they're not necessarily the number of tropical storms, but the intensity of tropical storms. I think the realization for many people who are used to looking out their window and seeing particular birds in their yard, and either different birds, or the birds they used to see are gone, seeing flowering occurring at different times. I think for a lot of people who are really in any way conscious of the environment about them, they're starting to see these changes themselves. And it's just that we have to just continue to try and help people who want to understand. Some people don't want to, but people who want to understand, I think we have to continue to point them to these various resources. In 1995, the IPCC, in looking at climate impacts, basically said, well, climate impacts are largely hypothetical. By 2001, on every continent, you could see them. So part of that is more that a lot of change has happened over the period of a decade or so that began in 1990 and 2001, but also that people are looking more closely. And I think anyone who looks at the environment today will see these changes.
Right, we're going to see if the technology is working for the overflow room. Can you come in, Alice Mason?
Should we go?
Right, have you got a question from there?
Not at the moment. We come back in a moment.
We'll take one. What did you say? We'll take one from the third one in from the gentleman on the third one in. Negotiate.
My name is Margaret Wilson, and I'm an art historian, which is nothing to do with this. But I have a cousin in Canada who is an intelligent, very
Sorry,
intelligent.
a little closer to the mic.
Okay. I have a cousin in Canada who is an intelligent laywoman, and I tried to talk to her and realised that we were just on such a different planet that there was really no point, because she was saying that the Greenland ice cap is not melting, and that any effects of global warming are caused by the sun. So there just was no point whatsoever in talking to her. And I think my question is, how can this kind of situation be addressed? And is it being addressed? I mean, I suppose that's on both sides of the pond, really, but she's in Canada.
Yeah, so the question is about, well, is Greenland accumulating ice or losing ice, and the solar variability? Again, unless you know the information that someone is using to form those views, it's very, very hard to work backwards. And if they said, well, here's this thing I read, then you talk about it. And I've had people come to me with stacks of material like this, saying, you know, I really do accept this body here. What's wrong with it? And you only have to go through paper by paper by paper and show the inconsistencies and oversights. The Greenland one is tricky because since people have been running climate models looking at the effect of a warmer world on climate from high latitude to low latitude, and Sir John was mentioning precipitation earlier, the models show, for basically the reason he gave, that we could expect more moisture in the atmosphere, and therefore more moisture precipitating over Greenland and over Antarctica. Antarctica is the coldest continent, it's the windiest continent, it's the highest continent, it's also the driest continent. And as you put more moisture into the atmosphere, more of that moisture can get into the interior of the continent. And the same with Greenland. And you would expect there to be more precipitation, more ice form. And that's happening. But what's also happening is we're losing it from the edges faster than gaining the middle. And now there are measurements being made, gravity measurements in space, which show how the mass of ice in Greenland is changing. So the dome may be going up, but the sides are going in. So lower elevation, we're losing it, gaining higher elevation.
Right, should we try next door again? Jonathan?
Yes, just a moment.
Thank you. I noticed from the abstract that accompanies this particular lecture that you mentioned in the very last sentence about the role of what sound like particularly shady special interests designed to manufacture doubt. I wonder if you might be able to comment a little on that and try to give us an understanding of where these interests are coming from, perhaps help mystify that the global scientific community will be able to combat these interests, which seem to be pretty powerful.
So special interests, and I mentioned is I saw this great billboard, this Exxon billboard at Heathrow yesterday, talking about wonderful things they're doing to clean up our air. And this is a report from last year's Smoke, Mirrors, and Hot Air. How ExxonMobil uses big tobacco's tactics to manufacture uncertainty in climate science. You know, there are a number of examples, and I testified before my U.S. Congress's House of Representatives on this report last year. And again, motives are, you know, we can only guess at them. But certainly for our largest oil and gas company to have played the role they have over a period of a couple of decades now, to fund groups of dubious credentials, and again, many of them morphed right from the tobacco industry, same people, same organization, changed the name and changed one word in the name, to generate sort of in-house documents that look like official reports, look like scientific papers, casting doubt on climate science. So this is basically it has cost us time. We have no time to waste. So John is saying this is an urgent problem. And when people say, well, what's the harm in having a good discussion? When the good discussion really poisons when these positions really poison the discussion, when you have, in my own country, representatives of the people voting in our Congress who are informed by documents coming from ExxonMobil rather than the scientific community, it's very, very frustrating. It's downright annoying because they are just costing us time in solving this problem.
Thank you. I think we'll take one last question. This gentleman's been very patient. I'm sorry, Colin, missed you. And then we'll pause for coffee.
My name is Mark Dowd. I work for a rather apocalyptic sounding organisation called Operation Noah. Looking ahead to the election and looking at the pronouncements made by John McCain and Barack Obama, how would you mark their scorecard on the climate change front?
If you had told me 4 years ago that in this round of presidential primaries in the United States, we would have people like McCain, Obama, Clinton, Richardson, Huckabee, Biden, others all saying the same thing, basically, disagreeing whether it's 78 or 90%. But we must get on this trajectory, Sir John, to not only 80% reduction in fossil fuel emissions by 2050. I would have said unbelievable. And I'll come back to why I think this sort of public opinion has shifted on this. The political leaders in the United States have not, on this issue, have not been at the presidential level. You know that. Not only in the last 8 years, but we didn't get nearly as much as we should have gotten from a Clinton and Gore administration moving us forward. The leaders have been mayors. Hundreds of cities in the United States now have pledged to get on these sorts of trajectories. There have been governors, coalitions of governors. And so I think our politicians running for the presidency are not leading yet. They're not in a position of leadership on this, even if they're elected. They're still following. They're seeing that there's enormous public opinion that is nudging them this way. So, comparing the two, Mr. McCain has a substantial track record. I've testified before the committees he chaired for the U.S. Senate. He was keenly interested in this problem. In year 2000, 2001, he was the only senator who was making a serious effort to inform the Senate on this. The McCain-Lieberman, then became Warner-Lieberman bill, up and down, down again, as Warner-Lieberman. But it's in each case, it's gotten better, each round. Serious cap and trade, selling the permits. Obama has made statements. He has some good advisors. It's very hard to know where he will go. He doesn't have a track record the way Lieberman does. But no matter who is elected, and this is going to be an issue for many of the other elections in this country, again, senators and representatives, and I think the United States will be in a very different position 1 year from now. I think in February next year, it's going to be a great time to celebrate our big AAAS meeting, the realization that we now have listeners in the White House who are prepared to look carefully at the science and make wise decisions for our nation and hopefully contribute the way we have it to the international dialogue on this.
Well, thank you very much. We'll